Okay, good morning. Welcome back. So today will be a bit more higher level than yesterday because we will see what is the structure of the code and what you need to know if you want to modify it while respecting the style and the rules. So we have 2 lectures on coding this morning and then 1 exercise session. But I'm pretty optimistic that the 2 coding lectures will be short. And so maybe after 1 hour and a half, we will be able to start the exercise session. So this is the program of the morning. I will go through the overall structure of the code, and I will insist on 2 technical issues, which are what are the rules for the dynamical allocation of indexes, and what are the rules for error management. This will require a little bit of concentration. In between, I will talk about the way in which input parameters are handled. In 5, I will give just general guidelines on what you should do if you want to add a new feature in the code. And then quickly, we will conclude with a short discussion on what you should do in order to get the Python wrapper updated with the last modifications of the code. And I will talk a little bit about the samplers that you can use with class. Okay, so we start with the overall structure of class, and I should say first, what is a module in class? So a module is first an include file .h that contains declarations and code file source.c containing all the functions. So you will always have the same name, of course, for the .h, for the .c, and for several other things. So each module is associated with one structure. Usually the structure has the same name as the module itself. And this structure has a very precise definition. It should contain all what the other modules need to know from this module, because they will only have access to this structure. And it should contain nothing else, because we want to keep it light. So anything which is used internally in the module but will not be used from outside should not go inside this structure, but should go in other structures or should be local variables of the functions. Okay, so in this structure, there are some fields, and they are declared in a given order in the .h. The first piece always is the bunch of parameters that should be initialized by the input module. So I repeat, in the structure of a given module, you have a list of variables. The first one are assigned by the input module. The other one will be filled during the execution of the module and will contain the result if you want. So a structure, in a sense, contains the input and the output of the module. Okay, so all these other fields in the structure are all initialized after calling a single function, which starts with the name of the module and then init. So in fact, executing a module only means calling init, nothing else. All the relevant physics is done in functions inside this init. So if you want to check how it works and you have opened your computer, I'm going slowly so you have time to, for instance, edit include /background.h. This is the header of the background module. And then close to the top of background.h, you will localize the declaration of the structure background. And then if you look what is in the structure background, at the beginning, you will see input parameters, which will be assigned by the input. And the rest is more interpolation tables and other quantities, which will contain the output of the calculation. It will contain, for instance, the big interpolation table with all the background quantities. And so all these other fields will be filled when you call just background init. And to see background init, you can go to source background.c and localize this function. Okay, I go on with the overall structure of a module. I will show you what is a list of modules here. For each module, there will be an associated structure with its input and output. There will be an acronym in which is always used to call this structure, the acronym of the pointer to this structure, and a summary of what it contains. So I show you first the first two modules. I already talked about the background module, so it's in background.c, and it works with a structure called background, struct background. But now when I'm inside the code, I'm calling an instance of this structure that will be called BA. So BA will be declared as struct background BA, meaning BA is an object of the type of a structure background. So BA is our structure in the code. But very often we refer not to the structure, but to a pointer to the structure. And then we put a P before. PBA means pointer to the background structure. So when you want to call a variable inside the structure, if you have the variable BA, it will be BA point and the name of the parameter. But if you have, and usually that is the case, you have the pointer, it will be PBA arrow and the name of the variable. And this is a syntax you find everywhere in the code. And so the goal of the background module is to fill a table inside BA that contains all the quantities, the background quantities, evolving as a function of time. We already played with this background table yesterday. There was a script in which we used the get background. Get background is a function in the wrapper that reads this table of background quantities inside the background structure. So this is a canonical organization of a module. The first one is a bit special. It's input.c. Input.c is not supposed to do a lot of physics, so it doesn't have, there is no structure input. Because in fact, the goal of input.c is to assign values to the input variable, which are at the beginning of all these structures. So this is why there is not an input structure. In fact, input talks with all the other structures and fill their inputs. But there is another structure which is very useful and which is also alone. So in this array, we have associated these two. This special structure is a precision structure. It contains all the precision parameters. And it's part of our coding chart to group all precision parameters in the same place. We would hate the idea of having precision parameters scattered all around the place because we would never know how to control the precision of the code. So the precision parameters are relevant for all types of calculation, background, thermodynamics, perturbations, etc. But they are never hard-coded and they are always members of this structure precision, which is then abbreviated in PR and the pointer is PPR. Okay, then we go on with, so this was a special module. We go on with other normal modules. Thermodynamics.c has all its variables in a structure thermo, abbreviated in CH. The pointer is PTH. And the goal of the thermodynamics module is to write a table, like for the background module, with all the quantities as a function of Z. For instance, the Thomson scattering rate as a function of redshift. The perturbation module is a big one. It's the one with the biggest number of lines. It's the one containing the most advanced physics. It's very important. So it's perturbations.c. The structure associated to it is perturbs, abbreviated in PT with the pointer PPT. And the goal of the perturbation module is first, as we said, to integrate the ODE, all the perturbation equation, and then to store not all the results, but the source functions, which are relevant either for the CMB or for the PK, or if you want all these matter and velocity transfer functions, they will all be different indices of these source functions. Next, there is a module which is called primordial. So far, there was a unique order. You cannot do the perturbations if you have not done the thermodynamics you cannot do the thermodynamics if you have not done the background. The primordial module could be moved around because so far it's like doing everything from scratch. Primordial.c. It has a structure primordial abbreviated in PM with a pointer ppm, and its goal is to write the primordial spectra. So in most cases, we are going to use an analytic function for the primordial spectra. And so this module is very trivial. It just reads from the input, the input module is going to fill in the primordial structure the value of AS and NS. And the goal of the primordial module will just be to fill a table containing values of AS, K to the power NS. That's in most trivial cases. But now when you start to play with isocurvature modes and tensors, the primordial spectrum does a few more sophisticated things. And finally, if you play with inflation, then the inflation simulator is coded here in the primordial module, which explains that it's also a long module. I did not check, but it might be the longest one after perturbations because it contains the inflation simulator that really integrates the background and the perturbations during inflation. The next one is called nonlinear.c. It is associated to the structure nonlinear, abbreviated in NL, with a pointer PNL. And its goal is to compute this nonlinear corrections factor. So to do that, the code is calling HaloFit. I will tell you this afternoon that we also have HM code implemented and we will release it soon. So after computing the nonlinear power spectrum, it stores this ratio. Yesterday I called these R, and here it's alpha, but it's the same. These factors are, for each time and wave number, the ratio of the nonlinear matter fluctuation by the linear matter fluctuation. So it's the square root of PNL over PL. And so these corrections will be used when, at the end, when outputting the nonlinear power spectrum, PNL, but also will be used to get a nonlinear version of the CMB lensing spectrum or the galaxy shear or the cosmic shear spectrum. After that, you go to the transfer module, transfer.c. So the goal of this module is to compute the harmonic transfer function. I don't like the name so much, and I will tell you about some renaming we have in mind later. I don't like it so much because transfer functions, you can call also transfer functions the perturbations which are integrated here and normalized to r equal 1. Here it's called transfer because it was an abbreviation for the harmonic transfer function delta L, but there are different types of transfer functions throughout the code. I think it's a bit of a mess, and maybe we will improve some names and some syntax at some point. So transfer.c uses a structure transfers, abbreviated in TR, with a pointer PTR. And so as we said, its goal is to solve the line of sight integral to go from the source function to the harmonic transfer functions. So this is where, for instance, Bessel functions are calculated. And then the module spectra.c has a task of outputting all the spectra. When I say outputting, in fact, it will just fill tables in its own structure, which is a spectra structure, abbreviated in SP with pointer PSP. And so after the execution of spectra underscore init, this structure will contain the linear and nonlinear pk, the CLs, and other derived variable like sigma 8, sigma 8 essentially. Okay, and the pk will be for total matter and for the baryon plus cold dark matter only if you have massive neutrinos. After that, there is only one remaining task. It's to compute the lensed CLs. So the lensing.c module is doing this, working with the structure lensing, abbreviated in LE, pointer PLE. So it will read the unlensed CL from this module and the lensing CL spectrum from this module, and it will do operations in order to infer from them the lensed CLs, and they will be stored in the lensing structure. And then the last module is only called if you run from a terminal. Because if you run from a wrapper, you don't need to do any more. The wrapper has functions that take information in these structures in order to give the results you want, either directly or with some interpolator. But if you are running on the terminal, you still need a module to read the results and write it in files, write them in files. So this is a goal of the output.c module. It has a very small structure which just contains information on the format of the output, abbreviated in OP, so the pointer is pop, and this structure contains a description of the format we want for the output. For instance, you always have the option of choosing between format equal class, which is a default, or format equal comb, which mimics the conventions of comb. So we have a different format that we find more logical, but if you are used to comb or you want to plug class in a code that was previously using comb, if you use format equal comb, you can always do it. Okay, very good. So how many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the 10 modules of class, which would reduce to 9 if we only use the wrapper. The wrapper doesn't know the last module. So coming back to the organization of each module, we talked about the structure, which is declared in the .h file. Now in the .c file, you find the functions. There is always the initialization function that does everything. Okay, as I told you, it's enough to call only this function to compute everything. But then at the end, you don't want to have memory leaks, especially if you are using class in a sampler. So you should free all the memory that was allocated by the init function. So there is a free function. So xxx, again, will be the name of the module. It's a suffix of all the functions in a given module, and it's the same as the name of the module itself. So for instance, in the linear module, this is called linear underscore init. Apart from these two functions, there are many others that are not called internal, external. This is just for the purpose of explaining, but they belong to these two categories. There are functions that are called external here because they need to be called from other modules. Usually, these functions know how to read the result in the structure and to pass it to the other module, maybe after some interpolation. So for instance, in the background module, you create a table of interpolation where you have a column for time and a column for each density and a column for h. And one external function of the background module will be background at a given time. So background at tau. It will take as an argument the tau you want, and in output, it will give you all the background quantities interpolated at this time. So this is a typical role of the external functions. The internal functions are only called by the init function when you really need to compute the physics for a given module. So how do you know if a function is external and internal? First, it's not very important to know because we make this distinction for our convenience, for readability. But from the point of view of a C code, it doesn't matter. It's not like in Fortran where you have private and public functions. Strictly speaking, all the functions can be called from outside. So when we say external, internal, it's just because we want to put some order in the module in order to understand it better. And the way to know is the order in which the functions are written. The external functions are always written first in the file. It makes sense because these are the functions which are exposed to other modules. So you should be very well aware of them, and this is why they are at the beginning. Then you always find init and free, and then you find all the internal functions. And when you become familiar with the code, you will see that the same naming conventions are used across the different modules. Okay. Yeah, so a remark, with all these rules, a module in the class code looks very much like what is called a class in C++. So you could say, why didn't you write the code in C++? So as I mentioned yesterday, we wanted to keep as many users as possible, and C is slightly easier to understand. People say also that it's slightly faster, or at least it's easier to be sure that it remains very fast. So we decided to do everything in C, but mimicking the style of C++. And so class means cosmic linear anisotropy solving system. But when we found the name, we thought it was consistent with our idea also from a stylistic point of view of mimicking these class features. So when you have a class in C++, you have a creator and annihilator function, and they would be this init and free. And the logic would be slightly the same. Okay, questions up to this point? No? So if you want to check this, for instance, you can go to the background.c file. And so we say that all the functions in a given module start with the name of the module, so background underscore. And they are always integer. I will explain why in a while. This is related to error management. So you can be sure that all the functions in background.c start by int background underscore. So you can just search for int background underscore and see what you get. And you will get indeed some external functions. The first one, I think, is background.tau. Then you will see the init, then the free, and then you will see something like 10 to 15 other functions, maybe more. Okay, and sticking to this logic, the main is incredibly simple. So maybe you don't want to look at the main already, because to really understand the main as it is on your computer, you need to understand error management, that we will explain in a while. If I was not interested in error management, I could write the main of class just like this. It would consist of just 22 lines, including the first and the last, because it would be the init function of each module in the right order, and then the free function of all modules in reverse order, because you want to free first what you have allocated just before. And indeed, this works. I mean, if you type this function and call it, it works. The class code is just this. By the way, on the t-shirt of yesterday, there were numbers behind the curve, and these numbers are just the main of class in hexadecimal format, so very compact. Okay, so what is interesting is to look at the arguments. So the arguments of the modules are pointers to the structures. So in fact, I exaggerate a bit because it's not just 22 lines. I skipped here the fact that I should have first declared these structures for the code to work. Okay, assuming that the structures have been declared, we have a pointer to each of them. The input module should read something. We will describe it later. This is your input file, or what is stored after you execute the .set in the Python module. And then it should know about all other structures, because as we said, it's going to fill the input part of each of these structures. So for instance, at this step, input init will fill the beginning of PBA, which contains the omegas, the densities. And it will fill the beginning of PTH, which contains, for instance, the helium fraction. And the beginning of PPT, which contains flags, saying if we have scalars and or tensors, and other things like that. Then the background module only needs to know the precision parameter and the background structure, because at this point the background structures already contain the input parameters relevant for the background, and the goal of background init is to fill the rest of the structure. So no need to pass other structures. Now, the thermodynamics module needs to know the precision parameter, needs to know the background structure because of the dependency. The thermodynamics evolution depends on the background evolution, and needs to know PTH, which contains its own input and its own output. Similarly, with perturbation, you need to add one more. The perturbation need to know the background and the thermodynamics. With primordial, it's a bit different. We need to know the precision. We need ppm because it's the input and the output of the module, but we don't need to know background and thermodynamics. And there is a PPT here, but I think this is an error. I will control. I don't think there should be a PPT, or if there is a PPT, no, we went through perturbation already. Yeah, I remember. It contains PPT because PPT knows if we want to compute scalars only or tensors only or both, and if we want isocurvature initial conditions. And the primordial module needs to know this. So it has a dependency on the perturbation, but it has no dependency on background and thermodynamics, so there is no PBA and PTH. Okay, then it goes on like this. The nonlinear module needs to know all the previous one, and so on and so forth. The lensing module has less arguments because it has limited dependency on some previous ones. And finally, the output module needs to know everybody because it will pick up output from all the structures. Okay, the free instead, for the free, you only need to pass the structure of the module because the goal is just to deallocate memory. And the information on, for instance, the size of the allocated memory is contained in the structure itself. So you only need one argument for each. If you would omit these and you would run in a loop or with a sampler, you would have memory leaks. All right. That's all for the overall structure. Do you have questions? No? Good. Okay, now, if you want to code while respecting the class style, which is not just to make some maniacs happy, but in order to get some efficient performances and some good readability of your code, you have to be a bit strict on the way to code your indices and to implement your error management. So let me explain. So indexing, so means just how to assign a value to each index in an array, is done everywhere across the code using always the same rule. I will take an example. Suppose we want to define a vector of background quantities. So the vector will contain the value at a given time of rho gamma, rho B, rho CDM, H, etc. So we choose an abbreviation of 2 letters. So far we could do everything with 2 letters. It offers enough combinations. And for instance, in this case, I will take BG for background. Okay, these have to be 2 striking letters that you don't find in many words, because sometimes you will want to search for BG, and if BG is in many normal words, you will have too many results. Okay, and then you declare all the indices you need, index BG, and then this could be rho B, rho G, Hubble, A for the scale factor, etc. You define all these indices in the background structure, which is in background.h. Because the other module cannot understand the table stored in the background structure if they don't understand the indices. So the indices are very important, and they must be declared inside the background structure. In this background structure, you should also define flags which say which species are present, such that we need to know if the flag is set to true or false in order to decide whether this index will be relevant for a given cosmology or irrelevant. So let's have a look of a few lines, for instance, in structure background. At the beginning of structure background, I told you our structures always start with input variables. So there are input parameters here. And these input parameters, which are assigned in the input module, include, for instance, omega 0 CDM, which is the big omega today of cold dark matter. After these input variables, it contains some technical fields like all the flags associated to each species. So the flag has CDM, means do we have cold dark matter in this model? And it can be, it's an int, but it will be assigned to values true or false. So in fact, it's more like a Boolean. Later on, you find another integer called index bg rho CDM. So it means index of the background quantity, rho of cold dark matter. And you find one for each species. And after the declaration of all the index underscore, you find bg size. So the acronym referring to this series of index underscore size. This is really the style everywhere in the code. And just to remind you, the goal of the background module is to fill up a table with all values. So at some point, you would find a double background table, and our goal is to fill this table. But in order to fill the table and to read it later, we need to know what is the value of all indices. Now let's look at another piece of code. It's a piece located in background.c in a function background indices. In fact, each module has an underscore indices somewhere. And the goal of the module is of the function here is to assign a precise value that you never need to know because you will only need the symbolic form of the index. So the goal of background indices is to assign numbers to all the indices that have been declared in the structure of the module. So inside the module, in fact, you will not find numbers. You will find, for instance, if y is the name of your vector of background quantities, you will find notations like this. Y PBA index BG rho CDM. So it's PBA a row because it has been declared in the background structure. So you can use a pointer to the structure and the arrow to call it. Okay, so once you are used to class, you think a bit as if the formulas were written in LaTeX, and you only look at the end. So if you see a class formula, you make abstraction of this, and you think, it's like if in LaTeX I had written rho CDM. You just have to look at this to remember that this rho CDM is part of an array that we call BG, and is part of the background module. Okay, so in background.underscore indices, you find an example of how all the indices are allocated dynamically. So it's important to understand this because a big percentage of class consists of this kind of declarations. So first, we have a region which decides which physics is relevant or non-relevant for this run. So in this case, if there is no cold dark matter, if omega 0 is CDM, has CDM will remain false. And there is another place before where all the flags are initialized to false by default. But now this line says that if we have cold dark matter, then we should put the flag to true. So this is done for all species, and later on, we are going to now finally assign our indices. I give the example of the index for rho, cold dark matter, and rho of the fluid. There is a running variable, it's a local variable that we call index underscore BG, and we initialize it to 0. And then for each species, we call the macro. You know what is a macro? It's like a little predefined script. It's all the macros in class start by class underscore something. All these macros are defined in command.h. And they are little scripts that are used in the pre-compilation. Before compilation, there is a pre-processing of the code, looking at the macros and replacing them by little scripts. So in fact, a macro is a way when you know that you will always have to write a list of commands, of lines, which are very similar to each other. It's a way to make notations more compact. So we are going to see several of these macros, and the first one we see is class define index. It's a macro we call every time we want to allocate these indices. And it takes 4 arguments. The first argument is the index we want to allocate. The second one is a flag which says whether we should really allocate it or skip it. The next one is a value of a running integer. And the last one is the size of the object we want to allocate in the array, and also is the amount by which we will increase this index. I explain. When the code arrives here, if there is cold dark matter in your cosmology, this index will be assigned the value index bg, which is still 0. And then when the function exits, index bg is incremented by 1. We would have put a 2 here if we wanted that this index refers to 2 numbers in the vectors. Then we do the same for row of the fluid. And now row of the fluid will automatically be assigned the value 1. Then it will go to 2. So we go through these macros, and at the end of all the macros, finally bg size is equated to index bg, and this will be the number of values that we have assigned. So by respecting this everywhere, you can keep a code in which the formulas look like LaTeX with only symbolic variables, and you never need to know if this has been assigned the value 7 or 15. Because of course, when you will read your input from outside, you will still use your variable y of row CDM. Because the structure which contains the table contains also the definition of these indices. So they can always be used when you read the result. Yes?
So every time then you want to fill, for instance, one of these quantities, for instance, row CDM, you refer to the index of the quantity. You never always the row CDM itself, right?
You always refer to the index here. You always write it like this. You never write a number.
And not only that, you never refer to row CDM, which is also a double in your code. Or for instance, H or H of the universe conformal or whatever. In effective, they're all doubles, and they all have their own index.
No, indeed. But here I'm talking really of the content of arrays. Okay, so in the background module, I need to have row CDM and row UR and etc. as grouped in a vector. And this is the index of the vector. But then you can declare, if you need to know n effective, it can be a double, and then this is not relevant. This is only relevant for the vectors.
Yeah, but I guess that what I don't understand is there's a duplicity in the variables. For instance, in the structure background, I see that there's a double H naught, but then there's also an index for H naught.
Yes, so double H naught is a variable inside the structure that will contain the value of H today. Okay, and it's an input parameter. The code needs to know this input parameter in order to initialize the system before integrating everything. Okay. Later on you will see the declaration of index bg row H, and this will be the value of H inside this vector at a given time. Yeah.
Okay, so the things with indices are just outputs.
Not necessarily. They can be used everywhere in the code, but very often they are the indices of the table in which you store your results. So for instance, the real goal of the background module is to fill this table. And this table, if you want to call one object in this table, you need to write some brackets and an index, and the index will be in this format. Yeah, yeah. But it's not always in the output, because, for instance, when we will integrate the perturbations, we will have a vector of perturbations. It will be index pt. And this vector of perturbation will be used to solve the ordinary differential equation system, but will not be stored in the output, where we will only store the sources. Yeah. Other questions? Okay, so I give you a few examples of this list of indices. In background.c, we have just seen the index of the table of background quantities. There is also an index which is not used in the output to answer specifically your question. It's the index BI. BI means background integration. So at some point, we need to integrate differential equations. If you remember the discussion of yesterday, in background, there are variables A, B, C. And the quantity that need to be integrated over time are the variables B and C. So for each of the variables B and C, I need an index that is used when I integrate my system. So index BI is then the index of this vector. So this vector is much smaller than this one. And this one is important for the output. This one is only used internally by the background module. In thermodynamics, there is the index TH of all the thermodynamical variables, and only this. In perturbations, there are lots of lists of indices. Index PT is the biggest vector in the code. It can contain hundreds of variables. It's really the vector with all the perturbations that we need to integrate over time. So it's very important. But then we need to loop over other things. For instance, metric perturbations. They are not part of index PT because they are not necessarily integrated over time. For instance, we say that in the Einstein equation, we have constraint equation. So the variables, the metric perturbation, for instance, h of the synchronous gauge or psi of the Newtonian gauge, are not part of the differential system, but they are part of the index of metric perturbation, which is index MT. Then we need to loop over scalar vector tensors, initial conditions, and the type of sources we want to compute. The source for CMB temperature, CMB polarization, matter power spectrum. So we need other list of indices. Index MD is the index over the modes, scalar vector tensor. So of course, if you do simple cosmologies with only scalar modes, the only one that will be assigned will be index mode scalars. Otherwise, you will have index mode scalars, index mode tensors that will both be assigned. Okay, for initial conditions, the loop over initial condition, you have an index IC, and then it's IC adiabatic, IC isocurvature CDI, IC neutrino isocurvature density, etc. TP is type of source. So as I said, it's the source of temperature, polarization, matter fluctuations, etc. And I told you also that the approximations used to integrate the system are formalized and are defined within an elegant framework. And for this, we have also indices running over the different approximations, because very often we have to loop over all the existing approximations, like the tight coupling approximation, for instance. So there is an index underscore AP underscore TCA. And there are many others. So in your .h file, you will see many of these. Yes?
So regarding the approximation, so what happens if you have transition region where you can apply this, like one of the two approximations, or they don't suffice?
Yes. So if you remember the plots of yesterday, the situation can be complex because you can have a wave number which goes through first approximation A and then B and then C, while another wave number will go through A and then C and then B. The order is different for all modes. So there are many functions dealing with this in a flexible way. So for each mode, the code will look when, for each approximation, there is a condition that defines whether the approximation should be used or not. Okay? For each wave number k, the code loops over the approximation and check what is the start and end time of this approximation. And then there is another function that puts in chronological order all the switch on and switch off events. And it cuts the time into little pieces. In each piece, you have a set of approximation which remains fixed. Then in each set, the integrations are integrated, they stop. And there is a function which knows that it stops because the third approximation went from off to on. It copies a vector of perturbation to a new one which is either bigger or smaller, and it integrates. And it does the same at each switching time. And so all this is dealt automatically for you. So if you invent a new approximation, you just need to respect the structure in which the other ones have been coded and to formulate a condition for using your approximation. For instance, decay rate bigger than h, for instance. Once you have formulated this condition and you follow our structure, the code will automatically decide when for each wave number you should switch on, switch off, and will automatically make this compatible with the other existing approximations. Yeah. This was a lot of work, actually. Yeah. Okay. Yes. Input. For the input, everything is managed by the input module. And of course, you can be defining your input in a file or through the wrapper with a .set command. The idea is that in whatever way to pass your input leads to a command step. And after this step, everything is treated always in the same way. The goal of the preliminary step is to file a structure that we call file content, abbreviated in FC. This structure is very simple. It's a list of names and a list of values, all in string format. So the goal before this step is to write in the structure, to say that the structure has a size maybe of 30, and that there are 30 strings, which are the 30 names, and 30 strings, which are the 30 values. The values can be numbers written in a string, or acronyms like TCL, PCL, or BBN. So if you pass your input in a file, the input is read by a function called input_init from arguments. And this function is a class parser. So a class has its own self-contained parser. It looks at the file, it eliminates the comments, it eliminates the line which make no sense. It searches for the equal sign, what is on the left of the equal, what is on the right of the equal. And it writes the result, which is supposed to be making sense, as a list of names and a list of values in this structure. If you use the wrapper, this will be done directly, because inside the .set arguments, you have a dictionary with already name, value, name, value, name, value. So this is very, very quickly interpreted and stored into this file content structure. So in any case, at some point, you have your file content, and you pass it to input_init. Input_init must call a few functions, and in particular, at the beginning, it calls functions that set all the default value of all parameters. All parameters are assigned a default value here, which can then be overwritten if the parameter has been passed by the user. And as I said, there is no need to you don't need to worry that you will not understand what the code is doing if you don't know all the default value, because I can tell you in one sentence, it will do lambda CDM with Planck best fit value and no complications, no massive neutrinos, no tensors, no non-adiabatic initial conditions, just plain lambda CDM. Okay, so after assigning the default value, input_init calls input read parameters. And input read parameters will loop over all the lines in the file content with all the names and values. And it will make an interpretation of this input and update the parameters that need to be updated. And this is where the logic is written. The logic, for instance, of shouting if somebody has passed both the big omega and the small omega of a given species. At the end, input read parameters has figured out the value of all the really relevant input parameters. What are the really relevant input parameters? They are those which are at the beginning of each structure, beginning of background, beginning thermodynamics. Because in order to run, class, strictly speaking, only needs to know these ones. So after all this logic, the code is able to assign the values of all these input parameters at the beginning of each structure. So for instance, maybe it will forget about the value of the CMB temperature, but it will store big omega gamma, which is what the code really wants to normalize the density of the photons. Okay, so there is one more complication, but it's very useful for users. It came into play in version, I don't know, 2.2, I think, so because many people were asking for it. It's a shooting method. So I'm going to explain a little bit later what is a shooting method. It means that in some cases you want to iterate over this function in order to guess what is the correct value of the input parameter given an information passed by the user. So we will see how it works in 2 slides. Now let us look at how the code deals with a normal parameter when there is no required shooting method. And I take the example of the dark matter density. So the goal at the end is to assign the value of the parameter omega 0 of CDM. This is needed by the background structure. We arrive here, we are in a line of the function, so this is inside the function input read parameters. Before arriving to these read input parameters, omega 0 CDM has been assigned a default value, which is 0. Why assigning another one? No, sorry, which is not 0, which is because this is a lambda CDM parameter. So the default value is from Planck. Okay. Then the code arrives here, and there is a macro class call that we will explain later, which is used for any function. So skip the class call. I will explain it later. It has to do with error management. So in fact, what is really called here is a function parser read double. You can make, for the moment, abstraction of this and of these error messages. I will explain it in a few slides. So in fact, here we have the function parser read double, which means try to read a double. So this is a function of the parser, trying to read a double in the file content. And the first argument is a file content. It contains your inputs. The second one is a string that we are looking for. And if this string is found, it will be written in this variable, and the flag will be set to true. Otherwise, it will be set to false. And the rest is for error management. So it does this, and so it means that if in your file content there was a big omega CDM, it will be written in param1. And the second line says that if there is a small omega CDM, it will be written in param2. And then here there is a class test. I will explain also this macro. The goal of a class test is to produce an error if the condition that we write at the beginning is true. So this class test means that if both flag 1 and flag 2 are true, meaning if your inputs contain both of these parameters, we must return an error and an error message. And again, the format of the error message will be understood later. If the code arrives to this line, it means that this condition was not met. So in this case, the code just says that if flag 1 is true, it means that param1 contains big omega. And this is what we wanted. So the background structure will assign the value of big omega CDM. If it is the other one that has been filled, flag 2, then param2 contains small omega. And so what the background module really needs again is big omega. So it will be assigned small omega minus small h square. And h has been written before. So in the input module, the order in which we write these kinds of blocks have an importance because there are some dependencies. This block requires that small h has been assigned before. So when we write the input module, we have to be aware of this. But when you write your input file, then the order is completely arbitrary because if you reshuffle completely your input lines, the code will automatically read them in the good order. So this is without shooting. For the shooting, there is an additional difficulty. The shooting, for instance, can occur when you want to pass as an input value sigma 8. Sigma 8 is a way to normalize your matter power spectrum at a given scale today. But for a Boltzmann code, it's horrible to be past sigma 8 because the Boltzmann code needs to start from some initial amplitude. And if you give sigma 8, the code doesn't know where to start from because sigma 8 is computed a posteriori. So in this case, we set up a shooting method saying that if the user passes a target parameter sigma 8, the shooting method will find the unknown parameter AS. And similarly, if you want to fit Planck, you want to use as a parameter the angular scale of the sound horizon. This is also an a posteriori parameter. So here we say that the user can pass a target parameter 100 theta s, and then the shooting will have the goal of determining the unknown parameter h. Here I give another example with decaying dark matter. You could be interested in defining a model through the amplitude of decaying dark matter today. But then the code doesn't know what is the initial condition for the decaying dark matter because you need to solve a differential equation to get it. So again, the user can pass a target parameter omega dCdm, and the shooting will try to find the initial value. This is used a lot, for instance, also in the quintessence case. If you want to assign the omega of quintessence, the code needs a shooting in order to find the initial value of the scalar field. Okay, so the goal of the shooting is to establish a map between target parameters, unknown parameters, and then to loop over possible values of the unknown parameter until the target parameter is reached up to a given accuracy. In order to make this efficiently, you don't want to waste too much time in the shooting. And usually the shooting works even if you don't call the whole class, and even if you don't use the full precision of class. So for instance, in this case, if I want to find what is the initial value of decaying dark matter that gives me the correct omega dark matter, I'm going to try many values of this, but why should I compute the CLs? It's irrelevant. I only need to go through the background module. And if I want to find the value of AS giving me a sigma 8, why should I compute the harmonic transfer function with a line of sight integral? It would be useless. So for each of these entries, we define a level. And the level is up to which the code needs to run for the shooting method to work. So here, theta s has to do with the sound horizon. The sound horizon is computed in the thermodynamical module. So you only need to go up to thermodynamics. For sigma 8, you only need to go up to spectra. For omega dCdm, you stay at the background level. And there are a few others like this. So if you need to add another shooting parameter, look how it's done for one of them, for instance, this one, and copy the structure. And you will see that you will need to define a new symbolic index for your shooting parameter, a target parameter, an unknown parameter, and a level. And the code will do the rest then automatically if you have respected this declaration format. Questions on this before I go to error management? Oh, I did not check the time. Did I go much over time? No. Very good. Okay, so we do a pause of 15 minutes. And after, I will do the second part of the coding lecture. The second part, in my opinion, will take less than 1 hour. And so we will have a bit more time for the exercises. Thank you.